So in the previous weeks for neuroscience, we've covered the basics of like what brain areas we have. We have covered how neuron works, that it has an axon for which it sends out signals, dendrites from which it receives signals, and that a neuron must spike in order to send out a signal, and that the way neurons communicate with each other is through synapses. And in these synapses, they either send neurotransmitters, or in the case of physical synapses, the neuron cell bodies themselves share the walls, and so they build up charge at the same time. So then we talked a little bit about plasticity, about brain disorders, and about senses and movement. Now, next step in that direction is to ask this following question. How do we even know how the brain works? Like, how do we know that we have these brain areas doing these jobs? And how do we know that this is how synapses work? How do we know, for example, at what electrical potential the firing happens in our brain? And more importantly than that, how can we find out more about our brain and how can we use that information to cure problems or even just enhance our performance, cognitive performance? Now, for all of this, we need some methods or some devices to measure how we are doing cognitively and also to just measure our brain. So that's going to be our today's theme. So it's all the brain devices, mostly known as brain-computer interfaces, but although not all of them, but generally. So some of them are for reading the brain activity, some of them are for changing the brain activity, and some of them can do both. So we'll talk about reading the brain, scanning the brain, and we'll also talk about stimulating the brain. Stimulating the brain is pretty much writing new content or just changing the mood and such. All right, I'll share the screen and we'll get right into it. Just a moment. As always, feel free to interrupt me at any moment. And yeah, let's begin. So, how do we look inside the brain so that we can more closely see, oh, here, this is where we do thinking, this is where we have vision, this is where we have hearing. So if I have a hearing damage, probably there's something wrong here. How do we know these things? Let's see. We have multiple, whoop, one moment. Okay, there. So how can we find out? There's multiple ways. So there's magnetic ways with magnetic encephalography. There's EEGs, which we'll get more deeply into in this lecture and in tomorrow's lecture. There's ECOG. There's a lot of different ways to basically read the brain and also to act on it. And the difference between them is that, well, first of all, some of them are easier and cheaper and some of them are harder. But more importantly, they have different levels of invasiveness and different levels of brain coverage. Now, what that means? Invasiveness means how much of a surgery do we need to do to apply this to you? For example, in the case of EEGs or in the case of MRIs, it's not invasive at all. It's basically just a headphone you wear or a device where you put your head. You don't need to open up your skull or anything like that, so it's much more comfortable and way easier to do. In the case of ECOG, for example, we have to put electrodes on the surface of your brain. So we have to open up your skull. Then inside it, we also have to open up a little bit part so that we can touch the surface. There are also some deep brain methods where we have to do all the way surgery and drill into your head, basically, and put the electrodes there. So uh, the more deeply we go into the brain, the higher level of resolution we can get, which gives us more brain coverage. So like we can do more with it, but at the expense that, well, it's less comfortable, more dangerous, and so on. So that's the essential trade-off between invasiveness and how much we can do with it. Now let's discuss each of the specific methods to see where they fit, how cheap and affordable, and how experimentable they are, and what they could give us. So first of all, as a rough map, you can see here there's different ways. We could record a single neuron cell so anywhere inside the brain. We could insert a group of electrodes called an electrode array, like a grid inside the brain. We could do experiments on the surface of the brain with ECOG. We could wear an EEG, like just a helmet, to scan our brain from the outside. But in that case, because of the skull, some of the signal will be lost and it will be less resolution, but we can still do a lot with it. And there's also a bunch of other tricks that we can use. We will get into each of these tricks now. But first of all, let's discuss some of the more popular companies dealing with these brain devices. One of them is Neuralink. So Neuralink is this company from Elon Musk that is currently making brain chips that let paralyzed people pretty much telepathically control computers, type text, and play video games. Currently, there's 11 people in the world who have a Neuralink chip in their brain. And basically how it works is, if you remember from the first lecture, we have an area here called the motor cortex. And basically every time we want to move our body, any part of our body, like our hands, our fingers, whatever, we have to send out our signals from the motor cortex. So in paralyzed people, the signals don't get all the way to their hands, but they are still created in the motor cortex. So this chip actually observes the motor cortex and from there figures out, oh, this person wants to move his hand, this person wants to move his leg, and they mapped it basically to mouse movements or to keyboard movements. And so because of that, now the patients can control the cursor or just type text actually faster than the world record in healthy humans. And so that's how they can basically regain some of the functions they lost because of paralysis. But this is pretty much step one for Neuralink. Neuralink actually has plans to then merge human minds with AI, make us a million times smarter, give us the ability to read 1,000-page books in a minute and stuff like that, which sounds like science fiction, but over the years we'll probably slowly see those happen. Also, one cool thing we should mention is that Neuralink is actually currently working on a project called Blindsight, which will give vision to blind people. Basically, it's the same principle. So the way vision works is that light hits the retina in our eyes, then it must travel through the optic nerve into the thalamus, and then the thalamus must send the signal to visual cortex. Visual cortex is at the back of our heads. So if a person is blind, it's either because there's a damage in the eye, in which case there are some medicines that might help, or there's damage in the optic nerve, in which case we don't really have a cure yet. But what Neuralink's Blindsight project will do is they will directly stimulate the visual cortex on the back of our head. So there's pretty much no need for eyes or the optic nerve. So they're going to slowly restore vision with that. They plan to have their first patient at the end of this year. Might be a little delayed, but yeah, it's in the progress. Okay, let's continue. So this is how the Neuralink chip's made. They have all these components they must safely insert in the human brain. And because it's invasive and we have to insert it, it's a lot more difficult. You have to get approvals, clinical trials, tested in animals first, and so on, which is a lot more problematic. So that's why this is less favorable than, for example, an EEG that you can comfortably put on your head and take off whenever you want. Like obviously this thing you have to insert surgically and remove surgically. All right. Now let's talk about uh, different levels of invasiveness briefly. So EEG and magnetic encephalography don't interact with your brain directly. They sit on top, so you don't have to drill anything in there, so they're not invasive at all. Then comes ECOG, which is less invasive because it sits on the surface of your brain. I mean, inside your skull on the surface of the brain, but not deeply. And then there's intracortical implants, which basically just means inside your brain, like the Neuralink chip, which, yeah, has to drill inside and is just big of a problem. So this is ECOG. ECOG is when you open up your skull, then you open up your meninges, which is a soft cushion that protects your brain from your skull. And then inside it, right on the surface of your brain, you put electrodes so that you can measure motor cortex, sensory cortex, or whatever you want, so that you can figure out your moves and anything. I will check the chat for any questions at any moment, so no worry about that. All right. So this is called ECOG, electrocorticography, which basically means, yeah, putting electrodes on the surface of your brain. And as for why electrodes would help, the rough intuition is that, as we remember from before, the way our neurons communicate with each other is that one neuron builds up electric charge and then discharges by sending signals to others. And this electric charge can be detected by electrodes, which just measure electric voltage. And that's how we can tell that this area of my brain is active, that area of my brain is active, therefore I'm doing this or I'm doing that, that kind of thing. All right, so how this works specifically, ECOG. So our brain has our head, there's a skull in our head, obviously, that protects our brain, but inside the skull there is also a layer of softer tissue called meninges, which is three layers. So there's the dura mater that's harder, then there's the arachnoid matter, and then the pure matter. And usually what happens is that this ECOG device goes between the dura and the arachnoid, so like somewhere right here. Because the closer you are to the brain, the better quality signal you can get, but also the more dangerous it is. So a good trade-off is generally that they are putting it somewhere between dura mater and arachnoid matter. Now let's quickly watch how synchron works, because this is also one of the more important things. So basically, two of the most leading brain device companies in the world right now are Neuralink and Synchron. So they both have invasive brain devices that let paralyzed people use phones, computers, and such. In fact, Synchron is partnered with Apple right now, and you can use iPhone or iPad even if you're paralyzed by having a Synchron brain chip. And let's just watch a brief video of how they work.
Some conditions affecting the nerve cells in the body can result in disability. Spinal cord injury, stroke, limb amputation, and motor neuron disease, or ALS, may all cause paralysis, or even loss of the ability to speak. The stentrode is a neural interface designed to overcome paralysis by creating a digital bypass from brain to assistive device. An investigational device, the stentrode is inserted via a catheter into the jugular vein and maneuvered into the brain without the need for open brain surgery. The sensors are built onto a self-expanding stent that engages into the wall of the vein and which is designed to maintain blood flow. Over time, cells may gradually grow over the sensors and incorporate them into the tissue. The sensors are placed immediately adjacent to the control center in the brain, known as the motor cortex. The patient may be paralyzed, but their motor control center can still be activated simply by thinking. The system is designed to transmit these brain signals out of the brain, out of the vein, and into a unit implanted under the skin in the chest. This unit is programmed to pick up brain signals continuously. The command center in the brain is now directly connected to software, and the patient would attempt to train their brain for direct operating system control by thinking. Direct brain control of a mouse, a keyboard, exoskeletons, and even vehicles may become possible. Technology to restore independence. Synchron's neural interface technology, enabling people.
So yeah, basically Synchron, similarly to Neuralink, is using just slightly different method that they insert their device through the jugular vein. It goes up into the brain and eventually connects to the motor cortex where we issue the commands for moving our body. And yeah, they try to tap into that to give paralyzed people the ability to communicate pretty much. Okay, so these are the invasive methods in a more direct sense, but there's also non-invasive methods that are more common, for example, in medicine. So, for example, this is fMRI. This is functional magnetic resonance imaging, and basically this one can capture more spatial information, but it's a little bit slower. And also it requires a lot more expensive equipment. So for comparison, the EEGs can cost like $1,000, but an fMRI can cost like $1 million. And so the way fMRI works is EEGs and the electrodes that we discussed before were measuring the voltage changes in our brain that happen because our neurons talk to each other. But aside from the direct voltage changes, there's also some indirect things we could measure about the brain. For example, if we know that I'm going to be imagining a lot of visuals, my visual cortex is going to be very active. And an active area of the brain requires a supply of blood because it needs a supply of oxygen. And as it happens, magnetic imagers can pick up on that because blood has iron and yeah, basically that can show up. And so the way fMRI works is it tracks the movement of blood through the brain. And because the brain takes a little bit of time to get there, it's a little slower, so it's a bit of a delay, but it has a better spatial resolution pretty much. So this is often used in clinics, but not as often used by just people experimenting on their own because this technology is just too expensive. There is also ultrasound, which is a little more interesting because it can access any area of the brain, even deep brain areas, even though it's not invasive. It's basically just a headset you put on, and it can both read the brain activity and also stimulate it. So, for example, there is a company called Nudge that is trying to stimulate specific brain areas to cure depression, to cure chronic pains, and just main different brain disorders simply by pretty much attacking pain centers, anxiety centers, and such in our brain. This is the device they currently have, which is quite bulky and uncomfortable. In fact, this is a wiring under the hoods. But they're currently working and they're trying to reduce it to a comfortable headset like this one. I think they might do it in about 5 years. They're led by Bliss Chapman, who was previously in Neuralink. So I think they have potential. And this is just one of the interesting areas. So another, which is actually the most common form, is EEG, electroencephalography. And this is most common because it's the cheapest and even like amateur people can use it. And there's many even open source designs, so you can see all the instructions of how to build it and how to use it online. And so basically the way this works is that in our brain, when neurons communicate with each other, there is electrical activity. And when a lot of neurons communicate, like in big activities, we can see this electrical activity and we can pick up on it. So basically, on the surface of our head, we place a bunch of electrodes, uh, and these electrodes can pick up voltage changes. And from those voltage changes, we can figure out, am I thinking about moving my hand, moving my leg? Am I sad? Am I angry? These things. We'll see how in just a moment, but for now, uh, there's different locations where we might put each of the electrodes on the surface of our head, and they have names. So generally, the middle line is called Z, subletter. The right parts of our brain have even numbers, left parts have odd numbers, and so C stands for central, which is basically for center of the brain. F is for frontal. T is for temporal, you have temporal lobe like around the ears. P is for parietal, which is basically at the back and up top of our heads. And then there's the occipital lobe at the back of our head where our visual cortex is. So based on where we put the electrodes, we give them names so that we can know where they are, basically. Now there's a EEG device called Neurosity Crown, which I like and which I have, which will go more into the coding side of in tomorrow's lecture. And I want to talk to you a little bit more about it, but basically it's an EEG. It has the electrodes that go onto your head, and it reads your brain activity, and from it, it can figure out if you're relaxed or active, if you're calm or focused or distracted, and it can also figure out if you want to move your left hand or your right finger or things like that. So focus, calmness, brain waves, movement commands. That's what it can do. So let's take a moment to talk about brainwaves. What does that mean? Uh, Basically, when a lot of our neurons get sort of synchronized, they fire at specific rates. And we measure these rates in hertzes. Basically, 1 hertz means 1 per second. So like if my neurons fire like 10 times per second, that means 10 hertz. 100 times per second would mean 100 hertz and so on. And generally, we can see in our brain that the faster our brain waves work, pretty much the more engaged our brain is. So when someone is in a coma or in like very deep sleep, they have delta waves, which is from 0.5 to 4 hertz. Then if someone is in dreaming or in trance, they are in theta waves from 4 to 8 hertz. If someone is relaxed or just distracted, they are in alpha waves from 8 to 12 hertz. If they Now in general everyday life, like right now when I'm just telling you this lecture, my brain will be in beta waves mostly from 12 to 30 hertz. And when we are very strongly focused, like when we're trying to solve a difficult math problem or when we're playing chess or very extremely stressed or something like that, we are in gamma waves, which is from 30 to 100 hertz. So pretty much by comparing, uh, for example, theta to beta ratio, we can see how focused we are. What that means is our brain will have different frequencies at the same time and different brain areas and different amounts. And we can pretty much check if our higher frequency activity is way more than our low frequency activity, that means we are focused. If it's not way more, then we are not focused. So pretty much we can just divide our beta wave amount by theta wave amount and get our focus level, roughly speaking. So that's how we might know this guy is distracted, this guy is focused, and maybe we can do something about that. this leads us to the phenomenon called neurofeedback, which is this strange phenomenon we know about, which is that, so imagine we measure with a brain device what happens in our brain. We take that data, we process that, and based on that, we do something on the screen. Then whatever we do on the screen, the person sees, and then again, we see their brain activity, and so there is this loop. What this allows us to do is this allows us to teach people how to control their brain pretty much. So, for example, if you're on the screen, we had a ball that can fly up if you remain focused. At first, you would see a ball not moving, but then as you become focused, you would see the ball move up, and you'd realize that some activity in your brain that you intuitively sense has caused this ball to move up. And this intuition develops and gets better and better the more you train. And basically, you figure out how to keep the ball moving up. And what you actually ended up learning was that you figured out how to stay focused, or, for example, how to fight your cravings. So, neurofeedback is a way that could be used to fight addictions of any kind because it basically teaches us how to gamify self-control. So it's quite a powerful trick, and there's a lot of research on if it can be used to pretty much cure any form of addiction in the world. And it might be the case, but there's research on it ongoing right now. Another strange thing that we should mention is called transcranial direct current stimulation. Don't worry about remembering the name, but basic idea is that we can put electrodes on your head and we can pass electricity to your brain through them. And sometimes some military agencies of the United States, for example, are researching this. This technology can be used to accelerate learning or focus in some cases. So, like, it can make you more focused or it can make you learn faster. So, it can pretty much boost your powers, so to speak. So, this is a very useful power to have. And yeah, that's something very actively explored by the United States military, by DARPA agency, and by others. And yeah, so basically, there's many different technologies for exploring and upgrading our brains. Let's discuss a little bit more about Neurosity Crown now, and then that's it for today's lecture afterwards. So, as we were discussing, those are the different forms of brain stimulation. I recommend you rewatch the video. I'll also link some useful videos and discussions about those. Um, and generally, so those are the methods that exist out there in the world, but pretty much the only one that is actually accessible to everyday people who don't have millions of dollars or don't have research grants is EEGs, so electroencephalographers. And the Neurosity Crown, for example, that we discussed before, is this device. And so you can see right here that it's made of these groups of electrodes. So you basically put it on your head like this. And then you connect to it with Bluetooth, with your phone, with your laptop. And what it can do is it streams your brain activity, and you can either take that raw brainwave data. It's not very useful directly, but you could do some algorithms on it, like you could check your beta wave ratio to your theta wave ratio, and from there figure out your focus level or something like that. Or you could even use a bit of AI machine learning, and you could train the device to recognize when you are focused, when you're calm, when you're anxious, or just different emotional states. And also, one cool feature it has is that some of these electrodes touch on your motor cortex that goes around here. And because of that, you can actually use this device to pretty much set controls on your computer, for example. So this device can tell you when you're moving your left, when you're thinking of moving your left hand or right hand without actually moving it in the real world. And you can write a bit of Python code to connect to this device and listen to it so that when it detects that you moved your left hand, you execute some code. And for example, an easy thing you could do is you could take a screenshot on your laptop every time you think about jumping, or maybe text something or click on some video, or just even press on moving right in a video game, for example, every time you think of moving your right index finger or left leg or anything like that. So basically, this device lets us basically connect our computer and programming to our brain and just make some useful things with that. We will discuss in tomorrow's lecture what useful things we can do with it and how we can actually use it in Python. But yeah, generally, I want you to know about this device. There are also other similar devices on the market. It's Neurosity Crown. I'll write in the chat as well. No worries about that. But yeah, let me like right here as well. It's called Neurosity Crown. So there's some American startup that are making this, but there are other ones as well. Like, let me just write out the other ones. There's OpenBCI, there's Muse, there's Neurosky, and plenty of others too. Like, there's plenty of these, but this is one of the best. But it costs right now around like $1,500. But there are some that cost like $300. I don't know if there's cheaper ones, but yeah, there's a lot of price ranges and they can do different things. But yeah, they're interesting to experiment with. We will discuss more programming side of it tomorrow, but yeah, I guess that's pretty much it for today's lecture. I just wanted to show you different techniques for measuring the brain, and I just wanted to tease this device that we'll use tomorrow. All right. Do you have any questions? Anything at all? All right, no worries. Okay, then that's it for today's lecture. I'll send the materials and everything that we went through. And yeah, that's pretty much it for today. I'll see you tomorrow. Thanks.